We saw in Lecture 4 that there is now excellent evidence for the existence of stellar mass black holes in binary systems with relatively normal stars. The visible star orbits an invisible object with such high speeds and in such a tiny orbit that by the process of elimination, a black hole is the safe, conservative conclusion. Any other alternative would be even more radical, any alternative other than a black hole. But it turns out that we have even more striking evidence for truly amazing beasts, supermassive black holes that live in the centers of galaxies, black holes having millions or even billions of times the mass of the sun. Well, I'll start this lecture with the very best evidence, which is provided by our own Milky Way galaxy. Now, we can't see our galaxy from the outside, but if we could, we think it would look much like this one here. A grand spiral galaxy stretching perhaps 100,000 light years from one ill-defined edge to the other, meaning that if you sent a radio signal to a friend at the opposite side of the galaxy, it would take 100,000 years for that signal, traveling at the speed of light, to reach your friend. Hardly a stimulating conversation. Our galaxy, we think, consists of several 100 billion stars, and if you look at it edge-on, it would look something like this one here, a thin disk with gas and dust in the plane of the galaxy from which new stars are being formed, and a bulge in the middle consisting mostly of old stars in a roughly spherical configuration. Our sun and our solar system is about half to two-thirds of the way out from the center. That's an ill-defined number simply because the edge of our galaxy is not a very well-defined quantity. But it's somewhere out there about 27,000 light years from the center. And if you look at the halo of our galaxy, the regions above and below the disk, you see a bunch of blobs. These are known as globular star clusters. They consist of something like 1 million stars all bound together by gravity into a roughly spherical shape like this. Beautiful clusters of old stars orbiting our galaxy. Well, when we look into the sky on a dark, moonless night far away from city lights, you see a beautiful band of starlight, the Milky Way. This is simply the collective light from thousands, tens of thousands, even millions of stars that we see when we look along the thin disk or plane of our Milky Way galaxy. When we look along the disk, we see lots of stars. When we look perpendicular to the disk, we see comparatively few stars. And so the Milky Way is well defined as a result of seeing this disk of almost countless stars. Ours is an edge-on spiral galaxy viewed from our position. So when you take a bunch of photographs and you plaster them all together in the sky like this on a photograph, you can see that we live kind of near one edge, and toward one direction you can see the central part of our galaxy with the bulge, and in the very center there, though you can't see it, we think there's a supermassive black hole. Well, studies of the orbits of individual stars in the central region of our galaxy are what tell us that there's this giant black hole in the middle. It has 4 million times the mass of the sun. And that's actually kind of a puny black hole as far as big ones go in the centers of galaxies. Some are billions of times the mass of the sun. Let's examine the reasoning. Stars very close to the center of our galaxy and other galaxies should move very rapidly in the presence of a black hole. In fact, the stars should move pretty rapidly even if there were no black hole there, because all the stars are pulling on all the other stars and they just cause gravitationally induced motions. But if in addition there's a black hole in the middle, then the gravitationally induced motions are even greater. So the idea would be that you'd measure a bunch of stars in the central region of a galaxy, see whether they're moving pretty fast or really fast. If they're moving really fast, that probably betrays the presence of a black hole. Well, when we look toward the center of our galaxy, we're looking in the direction of the constellation Sagittarius. And that constellation is best seen from the southern hemisphere of the Earth. It's higher up into the sky, and the region of our galactic center can appear almost overhead. So when you look at the Milky Way and the galactic center from the southern sky, in a dark, moonless night, it's just such a glorious sight. It's just a wonderful, wonderful sight. At optical wavelengths, we can't actually see the middle of our galaxy because interstellar smog, bits of particles that we call dust, and other stuff, gas and stuff, those things block our view at optical wavelengths. But we can see the middle of our galaxy at radio wavelengths, which are not so obscured by dust. After all, consider a foggy day. You can't see very far, but you can still hear your favorite radio station. For decades, we have known that there's a source of radio waves in the middle of our galaxy. It's called Sagittarius A star. A with an asterisk, but it's called A star. And you can see in this radio image, the central region where there's a white dot, that's meant to denote Sagittarius A star. You're looking at only the central light year or two here, 8 arc seconds. Now, a second of arc is very small. It's about the size of a dime seen from a distance of about 2 miles. So you're looking here at just the central tiny-most angle in the middle of our galaxy. But radio telescopes, especially for many years, didn't have very high resolution, didn't have very good clarity. And also, stars tend not to be bright at radio wavelengths. So you can see the stellar distribution in our galaxy better if you look at infrared wavelengths. Infrared wavelengths aren't as long as radio wavelengths, so they don't pass through the gas and dust quite as easily as radio wavelengths, but they still pass through more easily than visible light. It's sort of an intermediate wavelength of light. When you look at the sky toward the galactic center at visible wavelengths, you see all this dust, all this gas blocking our view. But at infrared wavelengths, you see a concentration of light. That's the concentration of stars toward the galactic center. So let's zoom in toward the galactic center. First, looking at optical wavelengths, we see a bunch of dust blocking our view. But if we then turn our attention to infrared wavelengths, we begin to see the glory of the Milky Way's center and all the stars that tend to concentrate there. Look at them all in the middle of our galaxy, seen at infrared wavelengths. There's a lot of them. This is just the central couple of arc seconds that we're looking at, yet there are all these stars that can be seen in the infrared. Well, for a number of years, some astronomers, such as Berkeley's Charles Townes, suspected the presence of a black hole in the center of our galaxy. The measurements of stars that he made show that they were moving pretty fast. But he was making measurements of stars that were kind of somewhat of a distance away from the center, so he couldn't really tell how fast stars move that are right near the center. Okay? You need to use other techniques to see stars that are in the middle of our galaxy because our atmosphere blurs out the images. There's turbulence because of all the different ways in which the air is moving, and this causes the images to shimmer. It's related to the twinkling of light. So when you look at the center of our galaxy, the shimmering sort of smears the stars together. You can't see them very well. Well, with a technique called adaptive optics, we can see the stars in the middle of our galaxy much better. You pass the light from the stars through a telescope, collecting the light with the mirror and sending it down to the focus at the bottom of the telescope. You can then look inside one of these boxes that holds instruments that can analyze and deform the light. Attaching the instrument to a computer, you can detect the image of the light as it's coming in. Here the light is coming in, bouncing off of various mirrors inside the contraption, registering on a detector, and then showing up on your computer. And without any correction, you can see the shimmering of the stars. The turbulent atmosphere is causing that. However, if you look at the wave fronts, that is the waves coming in of light, you can see that although they're deformed, if you bounce them off of a mirror and measure their deformation with a closed circuit like this, you can apply an inverse deformation to that little mirror, causing it to flatten out the corrupted incoming wave fronts, making them nice and plain parallel, as you can see. Then when those nice, uncorrupted wave fronts are detected by your detector and registered on your computer, you can see a nice, sharp image. That's the power of the technique known as adaptive optics. It's a wonderful technique that allows us to obtain a beautifully clear view of the skies over a very small spatial region. You can't apply this technique to wide-angle pictures of the sky. Well, when we apply this technique to images of our galactic center, we can see all these stars, hundreds of stars, in the central couple of arc seconds. And two sets of astronomers, one led by Professor Andrea Ghez at UCLA, and the other by Professor Reinhard Genzel, primarily of the Max Planck Institute in Germany, but he has a part-time position at Berkeley as well. Their teams have been monitoring the stars in the middle of our galaxy over the years. And here's Genzel's data, 1994, 96, another photograph in 2000. And you can see that the stars are moving, but it's kind of hard to tell exactly what's going on. So let's show over a decade of Genzel's data, and this time carefully connect the dots. What do we see? Wow, we see the stars orbiting something. Look at that, zoom. Look at that, zoom. We'll see it again. Look at, oh wow, zoom, zoom. These stars are orbiting some sort of a central mass that's causing their trajectories to change. They wouldn't be doing this if there weren't something there. And in fact, the stars are going so fast, and they go faster as they get closer to the center, that in fact, according to Newton's laws, you can figure out that there's one central, highly dominant mass that's causing all these motions, and the calculated amount of mass is 4 million times that of the sun. Not some puny little stellar mass black hole, folks. Wow, a supermassive black hole. Let's show the video again because it's so dramatic. I love it. There's a black hole, a massive black hole, lurking at this red cross. Well, that's appropriate. You'd want a Red Cross station anywhere where there's a massive black hole because, you know, the damage it could do to something that's nearby is amazing. So you need a Red Cross station there. Gez's group gets essentially the same results. She plots the orbits of the stars over the course of over a decade, and you can see those same stars zooming around some central, invisible point which harbors a gigantic mass. And two of the stars in particular are really interesting. Star number 2, for which we've seen a complete orbit of 15 years, and star number 16, which has a very elongated orbit passing very close to the invisible object. Star number 2, in fact, goes with a maximum speed of 5,000 kilometers per second, and it gets within 2 or 3 times the solar system's radius of whatever it is that's pulling on it in the middle. Just 120 astronomical units, 2 or 3 times the solar system's radius. Star 16 is even better. It gets within about 1 solar system radius of whatever is pulling on it, and at maximum it moves with a speed of 12,000 kilometers per second. This is compelling evidence for a black hole. You need about 4 million solar masses within a volume the size of the solar system. If you were to put millions of stars in there, they would be so blazingly bright that you would see them. And in fact, that situation would be unstable. It would gravitationally collapse after a short time to form a black hole anyway, even if it weren't a black hole at the time that you were looking at it. Indeed, star 16 comes within 600 Schwarzschild radii of this giant thing that's at the center. Well, those studies were based on pictures of the stars over the course of 15 years. Genzel's group has spectra of 28 of the stars, and the spectra show radial velocities relative to the observer, relative to the telescopes that are looking at them. And those radial velocities are so high that they confirm this conclusion that a giant black hole sits in the middle of our galaxy. Let's look at an animation zooming in toward the middle of our galaxy. You can see the orbits, the 3-dimensional orbits of the stars that have been monitored now for 16 years by Genzel's group. Look at them moving. The motions look slow here, but they're really fast on galactic scales, up to 12,000 kilometers per second. But with the pictures and the spectra, you get the full 3-dimensional orbits. Within the central light month around the black hole, Genzel has found that the stellar orbits are pretty random, like a swarm of bees. But farther out than a light month, the stars start coalescing into a more disk-like configuration, kind of resembling our own solar system. So something mixes up the stars as they get closer in. The measurements also give a more accurate distance of Earth from the center of the Milky Way galaxy. The present best distance is 27,000 light years. We are in a nice, stable orbit around the center of our galaxy. There's no chance of being sucked in. Don't worry, be happy. We're not going to get sucked in by the supermassive black hole in the middle of our galaxy. I tell people about it and they say, oh no, it's something to be scared of. No, it's not. Moreover, at our distance from the center, the supermassive black hole has almost no effect on our orbit. After all, within the sun's orbit around the middle of our galaxy, there's something like 100 million solar masses consisting of regular stars and dark matter and other things. Of that, only 4 million solar masses is a supermassive black hole. So from our perspective, who cares? Only the stars really close to it care that there's a supermassive black hole there. But we're far away, 27,000 light years away. Now, it's interesting that supermassive black hole in the middle of our galaxy has even made it into pop culture. In Stephen Baxter's 2004 novel, Exultant, there's a war between humans and aliens around this supermassive black hole. Not sure why they have to have it there, but that's where it is. Well, there's additional evidence for a black hole in the middle of our galaxy. There's flaring at X-ray wavelengths and IR wavelengths that has been detected. Material near the center is sometimes getting brighter and sometimes fainter. It's flaring up and down in brightness. Probably it's in an accretion disk, and there are clumps in that accretion disk. And sometimes those clumps glow more brightly and sometimes less brightly. The fact that there are variations on such short timescales suggests that there's a very small object there. Because as you can see in this animation, when we zoom down into the center of our galaxy, if there's an accretion disk that produces these flares and the accretion disk is small, then the flares will be relatively short-lived. After all, large volumes can produce long-lived flares, whereas small volumes can produce short-lived flares. So in fact, whatever is in the middle of our galaxy flaring, it's got to be pretty small. We see solar analogs for such flares. The surface of our sun sometimes has giant streams of gas shooting out of it like this. Solar flares. A lot of energy is released in a very short amount of time, probably because magnetic fields release their energy and change the energy into the particles streaming out of the sun. So really, these are the analog of solar flares on our sun. In particular, quantitatively, the solar flares, the galactic flares, suggest that the size of the accretion disk is maybe 10 astronomical units, something like that. And in fact, that's something like 100 Schwarzschild radii. That's about what we expect. Accretion disks are, in fact, 100 to 1,000 Schwarzschild radii in size. So when we see this flaring activity in the middle of our galaxy, we really think we're seeing clumps in the accretion disk that are growing brighter and fainter depending on whether they've collided with other clumps or whatever. But all this is occurring over distances of only 100 to 1,000 Schwarzschild radii from the giant monster inside. Now, most flares are pretty difficult to see. They're faint. But it turns out that 300 years ago, we think there was a really bright flare. And this was deduced by looking at X-ray observations of the galactic center. There was a cloud of gas 300 light years from the center that brightened and then dimmed in X-rays. And we think this was the X-ray echo of a flare in the middle. So there was a flare, the light streamed out, bounced off of a cloud of gas 300 light years from the center, and then came in our direction. So it was a delayed echo. Might Galileo have seen such flares 300 or 400 years ago? Probably not, because dust in our own galaxy blocks the view at visible wavelengths, and I don't think Galileo had X-ray vision, sorry. Well, the center of our galaxy turns out to have this black hole, but it's typical. You know, there are supermassive black holes in nearly every galaxy that we look at. Indeed, if anything, most galaxies have a bigger supermassive black hole than our own. You can apply these same techniques to other galaxies. You look for rapid stellar motions in the central regions, too rapid to be accounted for based on the gravitational mass of the stars themselves. But in these other galaxies, the stars are too far away to see them individually. We don't have the luxury of being only 27,000 light years away. So we can't see these individual stars. At best, we can measure the radial motions of the whole conglomeration of stars. The whole mass of stars in the middle is all kind of moving around. All these stars are moving around. And by measuring with a spectrum the absorption line widths, you can tell that really all that light is being produced by a bunch of stars having many different motions, and all of them together smear out the absorption lines in a spectrum, producing not sharp absorption lines, but rather broadened absorption lines. These are the smeared fingerprint of light from all the stars in the middle. And from the width of those lines, you can tell how fast the stars are moving. Now, you still have to have a pretty good view of the center. You don't want to have a view where stars far from the center are mixed with stars in the middle. This is where the Hubble Space Telescope comes in. It can get very clear images and very clear spectra of just the central region of a galaxy, showing that the stars are moving around really quickly. Now, with adaptive optics, we're beginning to do this also from the ground. But this is where the Hubble Space Telescope has a real legacy. For over 10 years, it's been making these measurements of stars in the centers of galaxies, and it has found that black holes are common in the central regions of galaxies. It measures not only stars, but also disks of gas, like the one in this galaxy. You can see that the disk of gas is rotating very quickly if you were to make spectroscopic measurements of it. And here's another one where, again, the spectra indicate that the disk is rotating very quickly, revealing the presence of a giant mass inside. If we zoom in toward the central region of a typical galaxy, we'll see the bulge where there's lots of old stars, but going way, way down in the middle, there's an accretion disk surrounding this monster, the supermassive black hole, containing 1 million or even 1 billion times the mass of the sun, voraciously swallowing the surrounding material. Holy moly. Well, one of the most massive black holes known is the 3 billion solar mass black hole in M87, the dominant elliptical galaxy in the Virgo cluster, about 60 million light years away. The orbital speed of gas in the central region of that galaxy is 550 kilometers per second, at a distance of only 60 light years from the center. When you measure this disk then, by looking at the emission lines and seeing that some are redshifted by 550 kilometers per second, some are blue shifted, and you play with the calculations, the formulas, you come up with this value of 3 billion solar masses. And this galaxy, M87, even has a jet of particles and radiation shooting out of it, shooting out from the center, reminiscent of the case of SS 433, a stellar mass black hole that also had jets of particles emitting radiation and flowing out from the vicinity of the black hole at a good fraction of the speed of light. So if we now zoom down into one of these elliptical galaxies that has not only a supermassive black hole and an accretion disk, but also a jet, we can see that from the artist's perspective, the jet might look something like this. It's emerging from the vicinity of the black hole, not from within the event horizon itself. I repeat that, not from within the event horizon. Many times the popular press gets this wrong. They say a jet shooting out from within a black hole. That's not correct. The jet of matter is being formed in the vicinity of the black hole by a still uncertain process. We're not sure how material gets accelerated to such high speeds, but it does, okay? Now, even these gigantic black holes, 3 billion solar masses, have Schwarzschild radii of only about 9 billion kilometers. That's about 60 astronomical units, about the size of our solar system or a little bit bigger. So even the biggest black holes aren't physically all that big. They're just massive, okay? The second best evidence for a supermassive black hole in the middle of a galaxy comes from the case of NGC 4258. This galaxy has a little tiny disk of gas in its central region, and that disk of gas mazes. It produces a maser, sort of like a laser, but at microwave wavelengths, short radio wavelengths. And from these mazing clouds, you can get very accurate speeds, and you can calculate that whatever's in the center of that galaxy causing the motions of those gas clouds, it's got to have 40 million solar masses. So that's the second best case for a supermassive black hole. We calculate that the mass isn't necessarily enclosed in as small a volume as in the case of the Milky Way, because we can see the central region of the Milky Way more clearly than in the case of 4258, but it's nearly as small a volume, so it's nearly as good a case as our Milky Way. Our nearest big neighbor, the Andromeda Galaxy, has a black hole in it, about 140 million solar masses. Zooming in toward the Andromeda Galaxy, we can see the central bulge, outside of which is the disk of stars. Zooming farther down into the bulge, we come to the nuclear region. In the nuclear region, stars are moving around really quickly, and you can tell that, in fact, those stars betray the presence of a black hole about 140 million times the mass of our sun. So this is really pretty typical. Well, when you look at all these galaxies, you see that a galaxy like M87 has a 3 billion solar mass black hole in it. And that galaxy is elliptical, doesn't have any spiral disk. It's mostly like just a bulge. It's like a bare bulge. A galaxy having a big bulge but also some disk, this galaxy, has a black hole that's less massive, only 700 million solar masses. A galaxy like the Andromeda Galaxy with an even smaller bulge and a more prominent disk has an even less massive black hole, only 140 million solar masses. And here's a galaxy with almost no bulge. It has a puny black hole, weighing in at only 300,000 solar masses. Now, this galaxy here, M33, has really no bulge at all. We've not detected a black hole either. The upper limit, the maximum mass that any black hole in there could have, is only 1,500 solar masses, so no supermassive black hole. Well, we see then that the mass of the supermassive black hole seems to be related to the mass and concentration of the galaxy's bulge. The bigger the bulge, the more massive the bulge, and the more centrally condensed it is, it turns out, the greater is the mass of the black hole. We don't know why there is this correlation, but it's clearly there. The big bulges, the centrally concentrated bulges have bigger black holes than the small bulges. And, this is telling us something both about bulge formation in a galaxy and about black hole formation. But we don't quite know what that something is. Does this correlation extend down to the globular star clusters? Well, there's evidence that it does, but it's controversial. Globular G1 in the Andromeda Galaxy appears to have a black hole having only 20,000 solar masses. And globular M15 in our own galaxy has a black hole perhaps of 1,700 solar masses. But, some of these mass measurements are insecure, and you could conceivably have a cluster of neutron stars in the central region. So we don't really know that these intermediate mass black holes having masses of only 10,000 or even 1,000 solar masses really exist. Maybe they do, maybe they don't. This is the frontier. We're trying to find them. Maybe they even exist down to even smaller masses of a couple of hundred solar masses. It's thought that maybe black holes having a couple of hundred solar masses first form early in the universe and act as seeds for the formation of these giant black holes. If you have a little one and it accretes material from its surroundings, it could conceivably grow into a really big one. So that may be the way in which you get these big ones, is from these small seeds. We have some evidence for the presence of these seeds. There are X-ray sources in M82 and other galaxies which are flaring. They get brighter and fainter at X-ray wavelengths, suggestive of an accretion disk around a small black hole. And here's another galaxy, M74, that has a whole bunch of X-ray emitting objects. You can see them marked in red on top of this optical, largely white image. One of those X-ray sources, an ultraluminous X-ray source, may well be a black hole having a mass of something like 100 solar masses. Again, that's still controversial. There are other possible explanations. But at least there's some tentative evidence for the presence of intermediate mass black holes as well. So we have shown in this lecture that supermassive black holes tend to occur in most galaxies, especially those having a large, roughly spherical bulge of old stars. What makes the supermassive black hole conclusion so compelling, especially in the case of our Milky Way, is that an extremely large amount of matter is concentrated in a volume smaller than the solar system. That's not easy to do without a black hole. And though we don't have direct evidence for the expected event horizons, our confidence is over 99% that these objects are indeed supermassive black holes. We just can't think of anything else they could be. And in the next lecture, we'll see evidence that some of these monsters are feasting on large amounts of gas that glows with a ferocious power.